Okay, let's talk about an element that's really common in HTML, meta character set UTF-8. What this character tag is doing is assigning a character encoding to the document. And there are many different ways to do this. Meta tag is just one of three. Character encoding is a lot of fun because we get to talk about very fundamental operations about how the computer understands text in one and zeros, the fundamental logic gates. Okay, so imagine we have a keyboard in this room and a printer in the other. And both the printer and the keyboard have agreed upon a particular character encoding. Let's say that they choose ASCII. ASCII is a good one to use. It's fairly simple. It was used in the 70s in America. And basically, ASCII is a cheat sheet. And it's saying, oh yeah, these characters over here, they're assigned a particular unique number. And both the keyboard and the printer have agreed. So when we go to the keyboard and we press a capital letter A, 7 binary digits made up of 0 and 1s are sent to the printer. The printer takes those 0 and 1s and derives a number. And that number is part of the cheat sheet, which says, oh yeah, that number, let's say it's 65. 65 is capital letter A. Now the two have communicated and the printer can then print A. Now, one thing here is a little bit of a mystery, and that's how that number is calculated. So that's what I want to figure out with you today, and it's actually pretty easy. It can be done on the back of a napkin. Okay, so we know that there are 7 binary digits sent to the printer, but what I haven't told you yet is that each digit has a value associated, and we're going to assign those values now. Starting on the right side, we have 1, and then moving to the left, we say the previous digit plus itself, so 1 plus 1 is 2. And we keep moving left, and 2 plus itself is 4. 4 plus 4, 8. 8 plus 8, 16. 16 plus 16, 32. 32 plus 32 is 64. Okay, great. Now, whether or not that value is calculated or not depends on whether that slot is on or off. So if there's a 1 in that slot, that value gets added to the overall value that gets calculated. If it's 0, it's off. So the first value is a 1 that gets counted, 64. There's a bunch of zeros, I believe 5 of them, and those all are essentially off and don't get count. The last digit is a 1 with a value of 1. So 64 plus 1, 65. And the ASCII cheat sheet says 65 is a capital A, and the printer goes ahead and prints A. Simple enough. Now, you can imagine that not every computer was encoded using ASCII. ASCII's great for English, but any other foreign-speaking language had no idea what to do with the ASCII characters and vice versa. So, to establish a standard, a worldwide standard, a group was formed called the Unicode Consortium. And they had one job: collect all the symbols in the world and assign them a number. Now, that doesn't specify exactly how to get that number, it's just assigning the number. And to get that high number, we have to kind of be creative. So in our previous example, we had 7 bits. If we stack the deck and put 1s in every single one of those, the biggest number that we can get is 127. That's nowhere near close enough the amount of symbols that will encompass every single language in the world. So this is the problem that UTF-8 solves brilliantly, and it's backwards compatible with ASCII. UTF-8 is able to be backwards compatible with ASCII by handling the first 127 characters essentially the same way, except it just sticks a 0 all the way on the left side. It goes, yeah, it's fine. I know that ASCII is 7 bits. I'm 8 bits. We're just going to stick a 0 in there and everything will be backwards compatible. Great. Now, but for anything over 127 symbols, things get very interesting, and this is where the variable width encoding comes in. Anything over 127 characters starts with 2 1s and a 0. That's the first main header. And the 2 1s represent that there are 2 bytes in this. So the second byte over to the right also has a header as a subheader, which is a 1 and a 0. Everything that is not considered a header is counted as a bit that will be used in the calculation to determine the end number that's associated with a symbol. So, for example, a main header with 3 1s has a total of 16 bits for calculation because the first main header has 3 1s and a 0, leaving 4 open bits, and then the 2 other bytes next to it have a subheader of 1 and 0, each having 6 additional bits open to the calculation. Let's look at a real-world example. And I think a good one would be the poop emoji. So let's learn how to insult our friends in Unicode. When I Google the poop emoji, I see something that doesn't make sense to us yet. I see some type of code made up with a U, and then a plus, and then a series of numbers and letters. This will make sense in a minute. Scrolling down, we can see that the UTF-8 binary looks like something that makes sense to us, right? It's got the main header, it's got 4 1s, which means it has 4 bytes and a bunch of sub bytes with that sub header element with a 1 and 0. And we can extract the bits that will be calculated, and we can calculate that, which should add up to 128,169. Yes. Now, here's where the thing that didn't make sense at the top of the page now starts to make sense. If we take that decimal and throw it in a hexadecimal converter, we get our 1F4A9 mystery solved. Now that we understand character encoding and how UTF-8 works, I mentioned earlier that there are 3 different ways to assign character encoding in HTML. The meta element with the character set is the most commonly used and accessible. It's right there in your HTML and you see it. But we have a chicken and egg problem. How can the character encoding get set within the document that needs to be character encoded in order to see the meta element that assigns the character encoding? I guess the browser can guess which encoding to use, and until it gets down a few lines and then it sees the meta UTF-8 element, it goes, oh, got it. Now I'm going to restart and use that character encoding. But we can do better than that. The second option is the HTTP header. Imagine clicking a link in Google, sending an HTTP request to a server. And by the way, HTTP can be thought of as a set of rules the browser and server have agreed upon or pre-agreed upon. And they both understand what the other one means when they talk. Okay, so the server gets our HTTP request. It sends a HTTP response. And in that response, we have our regular old HTML content. But along in that response is something called an HTTP header. And that's really important because we're allowed to send secret messages in the HTTP header. And one of the secret messages we can assign is something called content type. And we can specifically say, hey, this HTML I'm sending in this response should be encoded as UTF-8. And that's great because this encoding gets seen before the browser has to go in and look at the HTML itself. It's still a good idea to use the meta character set UTF-8 element in your HTML because of two reasons. One, it's good to just document. It's good to have there. It's a visual representation, especially if other people are going to be viewing your code. But the second reason is, what if this HTML file is run locally on your computer? That means there is no HTTP response or request. And the last backup that we have to assign a character encoding in this case would be the meta element. So it's always good to have there as a backup. Now, there is one last way, and it's fairly new, and I hadn't heard of it before researching this video, and it is called the bomb. And the bomb is very interesting, and I'm not sure that I would use it just yet in 2018, but we're going to talk about it. So, the bomb, as of December 2017 in HTML 5.2, overrides both the HTTP header and the meta element. So, if you go into your text editor and you go to save your file, and you specifically choose the Save as UTF-8 with bomb, then modern browsers will treat your HTML as UTF-8 encoded no matter what. Interesting. And what's interesting even more is that this works locally as well, because the bomb is actually saved in your HTML. I think co-opting this invisible character to enable UTF-8 is very interesting. Once all the server-side language and browsers adopt this, and it just works, like I have no hesitation that I'm going to get some little weird page breaks, things like that, which I hear people having trouble with the bomb. Once that all gets figured out, and the bomb overrides the HTTP and the meta element, and it's just more convenient, because it also works locally 100%, I don't see why this wouldn't get popular. But for now, in 2018, I'm sticking with my HTTP header response and my meta UTF-8 element. Thanks so much. I hope this made sense. Give me a like if you made it this far. I'll see you in the next one.